Hello everyone, this is Roger from Wave Computation Technologies. In this tutorial, I'm going to show you how to apply all kinds of excitation sources in the software Wavenology. The agenda of this tutorial is I first want to go over where to set up all the sources. Next, I will go through each of them. First is the lump source, including voltage port and spice port, and then the wave port, point dipole sources, and external sources including plane wave, beams, and near-field ingestion. Okay. To begin with, I want to first give an overview of where to apply the sources. So it's all included in the project tree. So you can see there's lump ports, wave ports, and sources. Okay. If you define the lump ports, right-click and create a lump port. If you want any sources, just right-click and create sources. So if you click this, you will see the dialog is popped up, and this is the type. It has electromagnetic dipole, plane wave, E-polarized, H-polarized, and Gaussian Basel beams, and also allows you for the near-field ingestion. So as you select different types of the source, you will see the parameter it's asking is changed. Okay, has some more control parameters, and also the near-field ingestion, you can specify files as well. So once you select this type, it always in the other section of the dialog, it always show you what kind of signal that you're going to apply to this type of source. So to here, I'm assuming that you've watched the video tutorial about our source signal, the transient signal tutorial. Okay. So let's get started for the first source, the lump port source. Okay, this is an example of the rectangular patch antenna. The lump port source is the most frequently used for the transient simulation. Basically, it just pick up 2 points in the 3D domain, and it will apply a voltage across this line, across this the 2 points you specified. So the interface to control to set up a lump port is like right-click, create a lump port. It says select 2 points in the 3D domain. So typically you just double-click. You see the 3D coordinates is there. Okay. So user need to control the 3D XYZ coordinates, and then it can be used as a source, as you can see here, as an observer. If it is a source, it asks you for the DC resistance, and then it always asks you for the pulses you're going to use. Okay. You are also allowed to add some delays. Okay, like for the first 10 nanoseconds, I don't want any signal, so it just delay for 10 nanoseconds. You can also scale your signal amplitude by using this value. Okay. So that's how you set up the lump port. In this case, I just have one lump port, and every boundary is open, and this antenna is radiating. So the result for lump port, you can see, is the S parameter is automatically calculated. So you see over the frequency from 0 to 20 gigahertz, this is resonant frequency, it's radiating, and some other higher modes. Okay. You can also check the incident voltage, scatter voltage, and total voltage on the lump port. So for example, this is the scattered voltage that this lump port is giving a transient signal, pulse coming in. This is the reflected ones. Okay. So that's all about lump port. Of course, you can have more lump ports, multiple sources coming in, but that is definitely allowed. But it depends on the problem that you have. Okay. The next source I want to introduce is the wave port. Wave port is actually a more complicated source. It covers through a surface area. Okay, and it will solve the eigenmode that is being supported in this entire surface and excite the field inside your problem domain. Okay, so the setup here, for example, is a waveguide. The four walls of this structure is PEC, so this is a rectangular waveguide. So I apply a rectangular surface wave port to feed in the source the fields. So as you can see, the setup here is a little bit more complicated. It's again, you can select observer or source and observer. Okay, select its position. okay, on the boundary of your domain that can be fit in. You can also change the size of the waveport. For example, right now it's just cover the entire X plus walls, but you can always shrink it down to a smaller size. And also the modes that can be supported, you can select, in this case, just one. And then always, as always, the signal that can be applied to this waveport. Okay. Again, delay and the scaling is also allowed. All right. So let's check the result of the waveport. First of all, I want to show the S parameters for a typical waveguide. So as you can see, if I zoom in around this valid area, at around the 3.8 gigahertz, the waveguide, the signal can propagate in, and beneath that, it's just cut off. Okay, so it's like a high pass filter. Okay, and if we check the signals at different frequency, of course we have the transient signals over here. So here is the transient signal for that waveguide. Let's take a look to this angle, and I don't want to show the field vector. Then I want to use a log scale. Then you start to see the signal is coming in. Only the supported mode can be transmitted through. Now the pulse is gone. Okay, so this is the transient signal. If you want to apply the frequency domain signals, for example, I want to take a look at 8 gigahertz. What is the field distribution looks like? Then it's being processed, and you can see all the signals can be shown. Okay, this is at 8 gigahertz. What is the field looks like? Now, if I turn on the field vector, you will see it's pointing this way, and if I change the time, you will see it's propagating through. This is the pattern, field pattern for 8 gigahertz. Okay, so it's on the propagating mode. Now, if I drop the frequency a little bit more, for example, 5 gigahertz, just click OK, and then the result will be shown. Here, 5 giga. Click again, you will see the wavelength is enlarged. That's why you have less periods along the waveguide. If you increase the time, you will see it's propagating again. Okay. And then let's take a look at the cutoff frequency. Below the cutoff, let's say 2 gigahertz. So I click OK. Then I have my result over here. If I turn it on, you will see all the fields. It's being reflected back. It cannot goes into the waveguide. Okay. So that's how the waveguide is not supporting this kind of frequency. So as you can see, the field is just oscillating at the beginning of the excitation port and can never go through. Okay. So this is about validation, simple validation of the waveport. Next, I want to show is the spice source. Right over here. Okay. So for example, this is a 50 ohm transmission line, and I have a source port and have another complicated source. So if I also define 2 points, make it line there, and I want to apply a very special source over there, I can use my SPICE circuit to define a complicated source. For example, I use my SPICE language to describe this. I have a pulse signal, which is a triangle pulse. I also have a comparator in the SPICE using the control source. And then I have another sinusoidal source signal. So what this circuit is doing is it's generating a pulse width modulated signal. Okay, if I show the source signal that's coming out from the SPICE circuit, you'll be able to see it's actually very complicated. So I have a examining signal that's called sinusoidal signal. Then I have a much higher frequency triangle pulse that is kind of modulating this sinusoidal source. So after it go out, it will be modulated with the pulse width modulated signal, which can be shown using the green lines right here. So as you can see, if the signal, let me turn off the other parts. If I turn off all the other signals, you will see as the sinusoidal signal magnitude goes higher, the pulse width is wider. It goes lower, then it's sharper. Okay, so that's how it's being modulated using this type of signals. I can use SPICE to generate this, and it can be simulated in the 3D as well. Okay, so that's about how to use SPICE circuit to generate complicated signals. And the next I want to show is the dipole source. So for example, dipole source is all included over here. Just create a source, here electrodipole and magnetic dipole. It asks for your 3D position, also asks for your polarization. So for example, I have two. One is pointing up, the other is pointing down, and it's a point source. At that particular point is singularity field. However, we will see the typical dipole radiation in this case. So after the simulation, I can show in the phase cut in this way. And if I use a log, you will see that, okay, the two dipole is radiating at different phases. Okay, one is at the strongest, the other is the weakest. So the way to achieve that is through adding the delay. Okay, and I'm using the sinusoidal source at 1 GHz to radiate the field. So by doing that, we can achieve all kinds of configurations of the two radiation source. Okay, so as you can observe, it's just radiating. All right, that's how the transient field looks like. Okay, so that's about the dipole source in 3D. Next, let's go to the plane wave. Okay, so the plane wave definition is actually not much difference than the dipole, but it's coming from outside. Okay, so the entire domain will have the field going through. All right, so for plane wave, for example, this is E polarized. You give the polarization of the E field, and then you give the spherical coordinates. We're asking for theta and phi angles in degree. Okay, so for example, it's 90 degrees in theta and 0 in phi. That will be this one right over here. The wave is propagating just towarding the x plus direction. Okay, so if I choose another field, I can customize it by setting the theta angle to be 45 degree. You will see it's pointing 45 degrees there, and phi is 0 degree. Okay, then I want to polarize H polarization to be along the y direction. So that's how exactly the indicator is showing. Okay, I also add some delays and have the magnitude as well. So you can have multiple sources coming in and control your delay as well. So in certain cases, this is very useful. So for demonstration, I just show you how the field looks like in this kind of simulation. So you will see as I go through, I'll just use linear scale. And you will see, okay, the first wave is coming as plane wave, propagating along the x plus direction. And after 3 nanoseconds, the second one propagating along this direction is coming in. They have some overlapping there. Now the other one is going through, and this one is going through as well. Okay, so that is how the plane wave looks like. It went through the whole domain with the pulse signal you specified. All right. So next, let's check the beams. Okay. So for beams, there's not much difference. It's very similar to plane wave. It's from the outside domain, and it will cover through the entire domain as well. But beams means you have a aperture. The field only propagates through the aperture, and it will have a distribution, energy distribution along the outside domain. Okay. So for example, the first beam I set up is this one. I use a Gaussian beam. So again, it's asking for the polarization. It's asking for the propagation direction in spherical theta and phi angle. And then it asks for a beam aperture size. Okay, the unit is millimeters. So if you specify 100 millimeters, it will show you in the indicator. This is how big your aperture is. The field will come in through. Okay, and it also asks for a beam axis position. That means this position can be changed. Okay, The aperture can be over here and over there. This is controlled by the beam axis position. Okay, and it's propagating along this direction as well. So I set it up another one. All these beams and other plane waves can be mixed together. So I set it up another one, like base L beam. So if I use the 45-degree and then this beam axis and make the aperture size larger, you will see it's two times larger than this one. And the polarization, the software is smart enough to automatically calculate the polarization vector. Okay, and it's normalized as well. I put a delay for this base L beam as well. Okay, so after the simulation, you will also see how the beams is different than the plane wave. Okay. Okay, so the snapshot is loaded. I'll move it to the this way, or I just use the preset view. Then I use the linear scale. Then I start to increase the time step. So as you can see, do it this way. All right. As you can see, the Gaussian beam is coming in first. The sinusoidal signal is being applied with 6 gigahertz. So the beam, it did propagate through the hole, the aperture. Now at this point, about 3 nanoseconds later, the base L beam on the corner of the problem domain is coming in. So these two are begin to mix together. So as the other one is still propagating through, the base L beam is coming in. Now it's beginning to interact with it. So superimposed together. Okay. So you do see the difference between Gaussian beam and base L beam. Different formulation is being applied, but the software are able to simulate all of them together. So this, for some optical applications, this is very useful because it represents the laser and other sources. Okay. So now that the two beams are winning through the domain and overlapped, you see all the beautiful ripples. Okay, so that's about applying the beams in Wavenology. So the last one is the most advanced feature that we implemented in the software. It's called a Nearfield ingestion. Okay, the reason we're having this is because in certain cases the analytical formulation of plane wave and the beams, Gaussian beam, base L beams, is not sufficient. A lot of the times the outside field is coming from the measurement. For example, the antenna radiation on an airplane outside, and it's touching the 6 walls of the domain. That is, no formula can accurately represent that, and most of the time it's obtained from the measurement. So we allow this feature. It's called Nearfield ingestion. All right. So it's the last option in your excitation type. If you select that, it's asking you for a file. Okay, you can load that file. So the file format is actually a standard format. It's called NFD format. So it's basically a frequency domain data. At certain frequency, you measure the field at the 6 walls at different locations, so it can be generated as a data. All right. Then you can measure several frequencies and put them in the same file. So Wavenology can recognize all these files. You can see this is very huge data at certain points. So it doesn't have to be matching the FDTD grid inside the software. So the software can resample or resample the data and doing the converted into time domain pulses as well. Okay. So for example, in this case, you give several frequency points. You give the field at all the locations from your measurement using this format, NFD format, and then the software can recognize that, load it in, and you will see this is a radome together with some receiving antennas inside. If I load the snapshot, okay, so put it in the right position, then begin to hide all the vectors, use lot scale. If I increase the time steps, you will see, okay, now the waves begin to coming in. It's not plane wave, it's not beam, it's from the real practical situations. Okay, as it's coming in, hitting the radome, and hitting the antenna. Now it went through. The antenna is still oscillating at certain frequencies. Okay, so this is how the external file, customized measure data, can be loaded into the simulation as well. All right. So that's all about the sources, the type of sources. I've covered all of this excitation pulses. Of course, you can mix all of them together because this is transient simulator. You can put all kinds of lump source, waveport, point source, and external sources. Put them together. The software are still able to handle all of them. So in the more practical applications, for example, you have an antenna radiating, you can apply a lump source, but simultaneously you have an outside field coming in. You can use beams and plane waves or even near field ingestion to model the simultaneously incoming field as well. And every other port source types can be mixed together as well. Okay, so that's all about the source tutorial for Wavenology. I hope you like it, and thank you for being my audience.